If you have a mass suspended like this, you're going to find that obviously it will have a weight as well. We need to consider the directions of the x force over here and the y force. So there's our x force, there's our y force. The x force is obviously pointing towards top left. What is the y force doing? Is it pushing against the block, or is it pulling away from the block? And we need to establish exactly what's happening over there. And the way I think of it is that, let's say the y force wasn't there at all. What would this block do? Well, it would obviously drop to about that position over there and hang straight down on x. So y, therefore, must be pulling towards the right. It says that these are suspended, and if they're suspended, that means that they must be in equilibrium. If they're in equilibrium, we'll have a closed triangle of forces, and we're going to say W is acting downwards, the Y force is acting to the right, head to tail, and the X force is acting up towards the top left-hand corner. So C is your correct answer. Soccer ball is dropped from a height of h above the ground and strikes the ground at a speed of v. We need to think of an equation of motion that's going to link those together, and it's going to be v squared is equal to u squared plus 2as. If we're dropping, we can immediately get rid of this u. So in essence what we have is, and we know, in essence what you have is you just have a direct proportionality. V squared equals 2as. You know that the acceleration on Earth is going to stay the same. It's going to be 9,8 the whole time. So I can ignore that, and I land up with v squared is proportional to the distance, which they've told me is h in this case. So what do they say? From what height must the ball be dropped to strike the ground at double the speed? So if I now need to double up this v, 2v, and it's going to be squared, what would have to happen to the h in order to keep them equal to each other is it would need to be 4 times the height, because you would have been squaring that 2 over there. So you land up with 4 times the height. Chad Leclos is a swimmer who is an Olympic world and Commonwealth champion. He swam his personal best for the 50-meter butterfly in a 50-meter pool at Tollcross. Now, the 50-meter pool is quite important because it means that he jumped in the pool there and he swam along and he ended over there, which means that his displacement was actually 50 meters. If it had been a 25-meter pool, he would have landed up going there and back, and therefore his displacement would have been 0. But it's not. It is 50 meters, and his displacement divided by his time of 23,29 seconds turns out to give you 2,15 meters per second. A space shuttle takes off from its launching pad, accelerating up into the air as shown in the diagram. The space shuttle accelerates because the upward force F is greater than the downward force of gravitational acceleration or weight. Which of the following statements describes where this F here comes from? And you need to remember that this is a reaction, an action-reaction pair. That is the reaction to these gases. So the gases come out the bottom of the rocket, and then the gases push back up onto the rocket. So the rocket pushes gases down onto the ground, the atmosphere, whatever, and those gases push up onto the rocket. So F is the reaction force, this F here, is the reaction force of the rocket's escaping gases pushing down. So it is a reaction to the downward push of the gases, D. An object is thrown vertically upwards by an astronaut on the surface of the moon. Which of the following graphs will best be a representation of the motion of that object? And what you've got here is acceleration time graphs. So what happens to the acceleration on any planet of any object? It stays 100% constant. C is your correct answer. You've got 2 charged particles and they exert a repulsive force on each other. The charge on X is plus 4Q. The charge on Y is Q. The magnitude of the force on particle Y, so there's a force being experienced by particle Y, and it's a repulsive force, so it's going that way, must be, and remember these forces are equal but opposite to the force that is on X. That's an action-reaction pair. They come about simultaneously. Remember that F is equal to K Q1 Q2 over R squared, or the distance between them squared. And that force is exactly the same on either of the two charged particles. Two identical conducting spheres, X and Y, carry charges of plus 3,2 and minus 6,4. What happens then is that, and we'll call that X and we'll call that Y, they then tell me that they touch. What is going to happen is you're going to add those two together. You're going to get minus 3,2, and you're then going to halve that between the two. So we even out the charges nicely, and you land up with minus 1,6 and minus 1,6 after the touching. During the touching, what happened to sphere X? Well, it used to be at plus 2 electrons, because remember, each electron is 1,6 times 10 to the negative 19 coulombs in charge. So you're going to find that it goes, instead of being plus 2, it is now minus 1. So it gained 2 electrons to fix that problem, plus another 1. So altogether it gained an extra 3. Notice what happened to Y. Y went from being negative 6,4 to being negative 1,6. So it lost 3 electrons. 3 electrons were transferred in that process. So the answer is B. The gravitational force of attraction between two asteroid balls is F. F is equal to G m1 m2 over r squared. The distance between them is halved. So I now halve that number over there. What is going to happen to this force? I've just done something there. I'm not quite sure what that means. So it means F is equal to G. A half squared becomes a quarter at the bottom, which is the same as a big 4 in front. So what's happened over here is this was that, which was the F. So my new force, force 2, is 4 times my old force, which was force 1. 3 identical bulbs are connected in a circuit. We're going to take out this one. What happens? Well, there's no parallel branch, so obviously B is going to get more current. So we're going to increase the current in B because it doesn't have to share it. There's no dividing that's going to happen over there. Okay? The other thing that happens is I am going to, by taking away a parallel resistor, I increase the overall resistance of the circuit. When I increase the overall resistance, if I had an ammeter over there, it would decrease. So in other words, this current decreases, and therefore A is my correct answer. Which one of the circuits below can be used to measure the current in a conductor? X, we want to connect the ammeter in series. We want to connect the voltmeter in parallel. The only one that does that effectively is the A.